Hello, and welcome to a new day of statistics. We're doing section 9.5, claims about two standard deviations, and then we're done with chapter 9. Okay, so we're going to be comparing two independent samples. Again, something like the variation for men's scores versus the variation for women's scores. So you would have these two independent samples. With this, you just need to know the sample size and the standard deviation. But there's a very important note. The way this test is set up, the S1 must be chosen, so that's the larger standard deviation. Or if there's a tie, of course it doesn't matter, but that's pretty rare. S1 has to be the bigger standard deviation. The test statistic takes S1 and squares it, so that's the first variance, divided by the second variance. This little formula is not in the calculator, so you will have to do that calculation on your own. But it's pretty fast. Pretty fun. The critical values being F, being for fun, means that we get a new table, table A5. It's got 2 degrees of freedom, one for sample 1 and one for sample 2. And notice that since up here it says S1 has to be the bigger one, that means you have the bigger number on top. That means you're going to be dividing by a bigger number by a smaller number. So the result is bigger than 1. That means it's always going to land to the right. There are no left tails. So let's practice using the table, F table, for this situation. So the claim is that standard deviation 1 is bigger than standard deviation 2, so this makes it a right-tailed test. This makes alpha equal to 0.05 in the right tail. Degrees of freedom 1 will be a 15, and degrees of freedom 2 will be a 14. Now, here's an overall picture of what table A5 looks like. Some important information. One is it's a right tail only. And as you look at that table, there's 2 possibilities. One page will look like this with 0.05 in the right tail, or it can have 0.025 in the right tail. Those are the only 2 choices. Then you look at degrees of freedom 1 across the top and try to find that. If you can't find it, you would go down here, and the next page would be connected, and you look over here for it. And then you look for degrees of freedom number 2 over here, and then you find out where the 2 intersect. So that's the general idea of that table. Now let's look at it in this case. So we're looking for degrees of freedom 1 is a 15 and then a 14. So we're looking for a 15 and then a 14. So if you look at the second page, here's the 15 and here's the 14. So that's at 2.4630. So it's 2.4630. That's the right tail. Now, let's go on to another one. This time, what if it said equals? Well, if it said equals, technically you're supposed to put 2 tails. 0.025 on one side, 0.025 on the other side. So the right side is going to have 0.025. So we're going to be using this one that says 0.025 in the right tail. Now we also need degrees of freedom number 1 is 21 and this one's 24. Also keep in mind with these tables, as always, if they don't have what you want, find whatever's closest. So across the top we're looking for 21, on the side we're looking for 24. So for 21, the best they have is 20, and then go down the side, and you'll see right here they have 24 exactly. So we go to where it's 21 and 24. So that's right here at 2.3273. 2.3273. Okay, now let's do a full example. So this doesn't have much of a story, just test the claim that these 2 groups have equal standard deviation. So group number 1, 32 people, a standard deviation of 14.3. Group number 2 has 33 people and standard deviation of 12.7. There are times in class when people would then say, hey, wait a second, group number 2 has the bigger one. But the rule was sample number 1 has to have the bigger standard deviation. It's not about sample size, that we're talking about standard deviation. So this one is set up right. This is the bigger standard deviation. The claim, H1 and H sub O, should all look familiar. This makes it a 2-tailed test, although we're not going to use the left tail. So this is going to be 0.05 that gets cut in half in the right tail and half in the left tail. That means that we're going to use in the right tail 0.025. That's the correct table to use. Then we need to be looking for 31 and then 32 for the degrees of freedom. So 31 is not possible. The best that we have is 30, so we'll use that. And 32, also not possible, so we're going to have to use 30 and 30. 30 and 30 means it's 2.739. All right, there's the setup. Now for the formula. Like I said, the formula is not in the calculator, but it's pretty easy. It's just this one squared divided by this one squared. So the bigger standard deviation squared divided by the smaller standard deviation squared. This turns out to be a 1.268, which is not big enough to go past the 2.07, so that means failed to reject. We did not prove anything. So we cannot make a conclusion. There's not enough evidence. Okay, one more example. This one does have a bit of a story. So compare my pre-calculus class with my calculus class. This is for the spring of 2014 data, in case you're wondering which semester this is. So for my pre-calculus class, 39 people, the standard deviation on exams, 18.3. Calculus has 34 people, standard deviation, 15.5. So it looks like the calculus people are more consistent, but is this enough data to actually prove it? So test the claim that the pre-calculus has more variation, so that's bigger than. Bigger than means it's going to be a right-tailed test, which means that we're going to need to use this table. Sorry, this is a little bit blurry. Didn't realize it till now, sorry. Anyway, it's supposed to be 0.05 in the right tail, because it's a right-tailed test. Then we're going to need to look for 38 across the top and 33 on the side. So 38 is not possible, but 40 is the best. And then 33 also is not possible, but if you go to where 30 is, that's a 1.7918. 1.7918. All right, so there's the critical value. Then take the bigger standard deviation and square it, the smaller standard deviation square it. Turns out that's only a 1.39. So that does not go past 1.7, it lands about here, which means, once again, fail to reject. We cannot prove that one class has more variation than the other.